So this is a great fact that I want to prove. Suppose that A divides B plus C, or sum, then A divides B if and only if A divides C. That is, A divides one of them, it divides the other, and if A doesn't divide one, it doesn't divide the other. Now, normally with an if and only if statement, you would go in two directions. You would assume this and imply, somehow conclude that A divides C. And then you would go in the other direction. You would assume A divides C and conclude that A divides B. And that would complete the proof. But you know what? A divides B plus C is exactly the same statement as A divides C plus B. That is, B and C are interchangeable. That is, when you prove this, you really prove that as well. Because you can say, oh, let B equal, in this proof, you do this proof, and then you say, you know what, in that proof, let B be C, and let C become B, that is interchange B and C, and this one is also true. But in the end, I'll prove it in both directions anyways. Now, what is this saying? Let's look at an example. Suppose A is 3, B is 9, and C is 6. Now, what does it mean for A to divide B plus C? B plus C, 9 plus 6 is 15. Well, what that means is, if you have, say, 15 marbles, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, for 3 to go evenly into 15, that is, for 3 to divide 15, if you keep taking away 3 marbles at a time, 1, 2, 3, you have at least 3 more left, take away 3. What it means is, after you keep taking away 3, 1, 2, 3, and then you don't have 3 more to take away, maybe you have 1 more or 2 more, but if 3 goes into 15, take away the last 3, that means there'll be none left over. You keep taking away 3. Really think carefully about what long division was doing. Just taking away a lot of 3's at the same time. When you did 25 into 9,250, 25 into 9, I don't know what I said. Let's write it down. 25 into 975. Okay, the answer I think is 39. You would take away the most number of 25s you can at one time. Maybe you never realized that. You take away 3 25s, which is 75. 22 left over, bring down the 5, and then you'll take away some more 25s. You would take away 9 more. Okay, so here you took away a number of 25s, 30 of them, because you really took away 750. And now 9 25s are 225. So you took away 9 more 25s from 975. And you're left with 0. Okay. Or another way of doing this. Don't do it this way, but it works. You can take away 25 one time. That's 950. Take away 25 another time. That's 2 times. Take away 25 a third time. That leaves you 900. And if you keep doing this, eventually you would have 5, 10, I'm not going to draw it enough. I'm not going to do it. But you'd have 39 in all. You will have taken away 25 39 times. So for example, if you were going to buy an item that's $25, no sales tax, or there is sales tax, after sales tax, it's $25. And just make believe there was a $25 bill. Well, if you have $975, you're going to have 39 $25 bills. So you can go and buy 39 of these items. That is what long division is. It's repeated subtraction. In my opinion, at least in my school, that wasn't taught very clearly to me. I mean, I knew how to do long division, but I had no idea that it was repeated subtraction until I went to college where my teachers cared and explained that to me. So now, we saw that 3 went into 15, or A went into B. Well, does A go into B? We saw, I don't know, maybe I said it incorrectly. We saw that A went into B plus C. That is, A went into B plus C. Now does A go into B? Well, B is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, we just saw that if I keep pulling 3 marbles out, eventually I'll have none left. Now, I'm just going to draw a line. Of course, if I keep taking away 3 marbles at a time, there'll still be none left at the end. Just because I drew a line isn't going to do anything. So, B has 9, so I'll call the top half B, and the bottom half, which has C, which has 6 marbles, I'll call that C. Now, since 3 does go into 9, why? Remove 1, 2, 3, remove another 3, 1, 2, 3, remove 3 more, none left over. So yes, 3 does divide 15 and 3 does divide 9. Now, we already know that if I continue to take away 3 more and 3 more and 3 more until I don't have 3 more to take away, there'll be none left. I did that before I drew this silly line. So if I take away 1, 2, 3, and 1, 2, 3, I have none left. If both of those statements are true, then 3 must divide 6. And it does, because I just proved it for this example. So let's try to prove this fact. A divides B plus C. Well, that means, so suppose A divides B plus C. That means that B plus C is a multiple of A, an integer multiple of A. M is an integer. And let's assume A divides B. So we're going to go to the right. That is, I start with this, and I go to the right, and I conclude that. Assume A divides B. Well, that means that B is a multiple of A. Now, A divides C, I want to show that C is a multiple of A. And I have these two equations. And the first one has C in it. So B plus C is MA. Solving for C, that is bringing B to the other side, it's MA minus B. But the second equation tells me that B is a multiple of A. That is, C is MA minus NA, which is M minus N times A. C is a multiple of A. That means A divides C. That's exactly what I wanted to show. Now, let's go the other way. Assume this. Assume A divides C. And I want to show this, which means B is a multiple of A. This means that C is a multiple of A. But I'm allowed to use this for both directions. So B plus C is MA. So this is just another way of writing C. So B plus C is equal to MA. Bring this to the other side. So B is equal to MA minus RA, which is M minus R times A. M and R are integers. You subtract integers, you get an integer. So B is a multiple integer of A. Well, this implies that A divides B. And this proof is now finished. Why? Because I assumed A divides B, and I concluded that A divides C. And then I assumed A divides C, and I concluded that A divides B. Excellent. Now let's look at something different. If A divides B plus C and A does not divide B, then I claim that A can't divide C, and something else, which we'll talk about in a moment. Here's another fact. Now, let's look at this. Let A be 3, B be 8, C be 7. So the sum is 15. And yes, 3 divides the sum, and 3 does not divide 8. 3 does not divide 8. Well, we know that if we have 15 marbles, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, we already saw that 3 goes into 15. Besides, you should know that anyway. But now we're going to partition it right here. The top half is B, which has 8 marbles. The bottom half is C, which has 7 marbles. Now, notice that when I take away 3, 1, 2, 3, there's at least 3 more in B to take away. I take it away. And now, although there's some left, there aren't in B, there aren't 3 more I can take away. That is, B does not divide, 3 did not divide 8. So I'm going to show that 3 does, so these two imply that 3 doesn't divide 7 either. Because in C, which has 7, I will take away 1, 2, and 3. I will take away another 3. And look at this. I have 1 left over, which isn't enough for me to take away 3. So 3 doesn't divide 8 either. 7 either. Okay, 3 divided 7 plus 8. 15 is 7, or let me say 8 first. 8 plus 7. 3 did not divide 8. And then we just showed that 3 doesn't divide 7 either. But we know that if I keep removing 3, that there should be none left. Well, of course, this is still going to be true, and it is true. I do have 3 to remove. 1, 2, 3. Now there's none left. So where did these 2 come from? Well, that was the remainder for B. That was the remainder. A did not go into B. That means that B is a multiple of A plus a remainder. Okay, and A does not divide C, which means that C is a multiple of A plus a remainder. And we just saw that when we added these 2 remainders, we got A back. We got 3. And RB plus RC must be 8. The 2 remainders must be 8. Why? Because then, since there were some left from B, the group of B, since there was some left when I divided B by A, and there were some more left when I divided C by A. Since A has to go into the sum, then there better be A left over. Just like here, there was 3 left over. So that's the second part. So I'm going to assume those two statements on top are true, 1 and 2, and then I'm going to conclude that these two statements are true. Okay, so proof. Suppose A divides B plus C and A does not divide B. Okay? So this statement means that B plus C is a multiple of A. And this statement means that B is a multiple of A plus the remainder. Plus the remainder. Call it R. And of course, when you divide by A, the remainder is always in between 0 and A, and it can even equal 0. But it only equals 0 if it equals 0, that means B is a multiple of A, which means that A divides B. But that contradicts this. That is, R is bigger than 0 and less than A. Okay. You know what? I don't know if I'm going to be sorry I did this, but let's call this R sub B. Now I want to show that A doesn't divide B. A does not divide C, I meant to say. That means that C is a multiple of A plus a remainder, which is not 0. Well, I have two equations. I have this equation and this equation. One of them has C in it, which is good. Solving this for C, C is MA minus B. It's MA minus B. B is MA plus RB. Something's wrong there. Okay. Silly, not an error, but this means that B plus C is a multiple of A, and I choose M to be the multiple. And here, B is a multiple of A plus a remainder. I accidentally used the same multiple, M. Let's change it to N. So this is MA minus B, NA plus RB. Well, this is MA minus NA minus RB, which is, grouping the first two, is M minus N times A minus RB. Okay. Now, let's write this down. So C is equal to this. It's an integer multiple of A minus RB. Minus. That means the remainder is, quote, negative. We want the remainder when we divide by A to be between 0 and A. Negative, we know that RB is between 0 and A, but not negative RB. So let's just note something. 0 is less than RB, which is less than A. Okay? Now, if I take away RB from all sides, if I take away RB from all sides, I don't care so much about what I just wrote down, but this is less than 0, which is less than a minus rb. Now we know that rb is positive. So if you have a and you take away a positive number, you have to be less than a. I don't care about this. I care about what's left over. Namely, a minus rb, which is in the middle, is bigger than 0, but less than 8. Just like a remainder should be. So I'm going to add a here, and I'm going to take away 1a from there. So C is m minus n minus 1a's plus a minus rb, where that's my remainder. So let me just get rid of this side work. Actually, it's not side work. It really needs to be shown, because otherwise one would wonder how, don't you think the remainder has to be between 0 and a? Well, I showed it. Okay. But this number right here, that's my remainder from C. So what is the remainder from okay, there is one other thing. I think I got into the remainder, this part. But did I show that A doesn't divide C? Okay. So this last line, C is a multiple of A plus a non-zero positive remainder, which is less than A. This means that A does not divide C. Okay. Now, kind of running out of space, but we'll pull it off. What is RB plus RC? Well, RB is just RB. That's the remainder of B. How much is RC? Well, it's A minus RB. A minus RB. The RB's cancel out and you just get A, which is exactly what you wanted to show. That the remainder of B plus the remainder of C is A. And we proved it. It's all there, folks. Carefully review this video. It's a good proof. You should know first, you should understand, at least understand this. And understand that the remainders upon division by A, the remainder when you divide B by A plus the remainder when you divide C by A must be A. Only if A goes into the sum and A doesn't go into one of the numbers. We proved that if A goes into the sum and A doesn't go into one of their two numbers, B or C, then A doesn't go into the other number. That's already proved. Now, does the remainder of B plus the remainder of C always have to be A? The answer is no. The answer is no. If A goes into B plus C and A divides B, which we already know from the previous theorem, that means A also divides C, then the remainder from B will be 0, plus the remainder from C would be 0, because if A goes into B, the remainder is 0. If A goes into C, the remainder is 0. So if it goes into this sum, if A goes into the sum, either the sum of the remainders will be 0, and that only occurs if A goes into one of the numbers, which we know means both of the numbers, or you get the sum of the remainders to be A if A does not go into B, which would, from our previous theorem, says A doesn't go into C either. So if A doesn't go into B nor C, but A goes into the sum, then the remainder will be 0. It will be A. If A does go into B plus C and A goes into B, which guarantees us that A also goes into C, then the sum of the remainders will be 0. It'll either be 0 or A. Again, only if R A divides B plus C. So, can we get something less than a positive? The answer is sure. 3 does not divide 16. Okay, 3 does not divide 16. Okay, so you have 16 marbles, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I partition them somehow. Look like 3, 5, 8, 9, and 7. 9 and 7. Okay, so we're dividing by 3, so the remainder should either be 0 or 3, I said. But I also carefully said that's only if this number goes into that number. Well, 3 goes into 9 means the remainder of when we divide by 9, when we divide 3 into 9, will be 0. Okay, but 3 does not divide 7, which means the remainder in this case is 1. 3, 6, is 1 left over. Okay, so here, the remainder of 9 plus the remainder of 7 is 1, which is not 0 or 3. It's neither of them. Okay, I could have picked better numbers, maybe, I don't know, 4, 5, and 11. Say there were 5 here and 11 here. That's also 16. Well, 3 does not divide 5, but the remainder is 2. And 3 does not divide 11, the remainder happens to also be 2. So you have 4. But then you take away 3, and the total remainder will be 1. Well, here I had the remainder being more than 3. I had, let's just leave it that way. The sum of the remainders was even more than 3. And that's because it didn't divide the numbers. The sum of the remainders is 4. It's actually more than 3. And if you take away 3, you'll get the true remainder of when you divide 3 into 16. Okay? 16 is a multiple of 3, 5 3s, plus 1. That's the final remainder. Okay, well, we got a remainder of 4, but you take away 3 and you get a remainder of 1. If you like, that finishes the video pretty much. If you like math like this, please subscribe to my YouTube channel. Leave comments below. Tell your friends and teachers about this channel. And most of all, have a great day.